composition of functions, for some reason it's like one of my favorite things. Composition, we want to think about what that word means. When you compose something, you're really creating something, you're putting something together. When you compose two functions, that's essentially what you're doing. You're putting two functions together. We're applying one function after another function. Apply one function after another function. So to diagram this out, let's say we have some input value. Let's call our input x. We like calling our input x. We apply some function f, and we get some output, which we would call f of x. If we have a composition of functions, we can now take that output as our new input, and we can apply a new function. Maybe we call that function g. So now we have g of our input, but our input was f of x. So now we have g of f of x. This is really the crux of why function notation is so important. If you try to explain what to do with this without using function notation, with using like y's or something, it gets really complicated to explain. So it's really important that we understand f of x is our output when x is our input. G of f of x is our output when f of x was our input to a new function g. So now this is our g output here, g of f of x. Notationally, you'll see that written as g, little circle, f of x. And that means compose g after f. We're going to first plug into f, and then take that output and use it as your input for g. We can also write it as we saw right above, g of f of x. You'll see both of these notations. It's important to be able to recognize them. So what you'd want to do is evaluate your inner function first, evaluate f of x first, then plug that into g. Let's see an example. How about f of x being x minus 2, and let's let g of x be x squared. And let's say we want g of f of negative 5. Well, first, I like seeing it in this notation. A little bit easier for me because I can see which function we're working with first. We're working with f of negative 5 first. Okay, f of negative 5 says take negative 5 and subtract 2. That's what our function rule is. Negative 5 minus 2 is negative 7. So now we had g of negative 7. Negative 5 minus 2 gave us the negative 7. We're using that output as our input for g. G of x says take your input and square it. So what we really now want to do is negative 7 squared. We're applying each rule. And we get 49. So g of f of negative 5 equals 49. I wonder if we can compose the other way. I wonder if composition is commutative. Let's try it out. F of g, do we think it's going to be 49 as well when we input negative 5? Let's see. F of g of negative 5 now says g is our inside function. We have to evaluate g of negative 5 first and then plug that output as our input into f. The rule for g says take your input and square it. So let's do that. Negative 5 squared, well that's positive 25. So we now have to evaluate f of 25. Our rule for f says take your input and subtract 2. 25 minus 2 gives us 23. So we can see these are not the same, 49 and 23. That just means that composition is not commutative. Not commutative. The order definitely makes a difference. Let's try it in general terms. What if I just wanted g of f of x? G of f of x, sticking with those descriptions above. G of f of x. Well, now we're not plugging a specific number in. We're going to stick with x. Let's see what that might look like. F of x was x minus 2. So what we really have is g of x minus 2. I just replaced f of x with x minus 2. They are equivalent. Our rule for g says take your input and square it. So now we have x minus 2, that quantity, squared. That's g of f of x. We just found it in general terms. Let's try f of g of x. Let's see. Our rule for g of x was x squared. So now we want f of x squared. We just replaced g of x with its rule, with its description, x squared. F of x squared, let's see. Our rule for f says take your input and subtract 2. So we're going to take our input, which is now x squared, and subtract 2. And now we can really see, oh yes, these numbers are, these functions are not the same. The quantity x minus 2 squared versus x squared minus 2, those are definitely not the same thing. So that should make sense that we didn't get the same numbers right above. Cool. Let's think about domain. Anytime we compose one function with another, we know that there might be some domain issues. So let me think about what we're doing. We had f of x was a line. There was no restrictions there. Domain was negative infinity to infinity. And g of x was a parabola, just a regular quadratic. Again, no domain restrictions, just negative infinity to infinity. When we sort of composed one with the other, in one direction we got a quadratic, and then we got a different quadratic. So there's still no restrictions on either of these. The domain for each of these was just negative infinity to infinity. Well, let's try this one. How about let f of x equal the square root of x plus 3. And let's let g of x equal x squared. And we know something funky is going to happen here because the square root function does not have an unrestricted domain. I know that if we're trying to graph this over real numbers or think about these functions over real numbers, what's under the radical has to be non-negative, which means our domain for just f of x would be negative 3, including negative 3, up to infinity. So when I compose this function inside something else, I have to remember that. So let's try g of f of x. Let's see. F of x was root x plus 3. So I'm just going to replace f of x with root x plus 3. And g of x is take your input and square it. Take your input, which was root x plus 3, and square it. And you'll realize the square root of something squared, well, that's just itself. We have to remember absolute value, though, back from 7.1, because we do have the square root squared, so we know that we can't ever end up with something negative there, so we do need the absolute value of x plus 3. And we have to remember that we applied f of x first. We did f of x, and then we plugged that into g of x. So our domain here is actually restricted. We actually are not allowed to plug in anything except negative 3 to infinity to this function. If you just look at this function, it's an absolute value function. You might say to yourself, that has an unrestricted domain, but we can't forget where it came from. It came from squaring a square root function. It came from back here. So we have to always remember the old domains when we're evaluating new functions, when we're figuring out what our new functions are equivalent to. And that's really the trickiest part of this whole ordeal, I think, is remembering where the stuff came from to know if our domain was restricted or not.